Hello, we are continuing on our journey through understanding the nature of light. We've looked at evidence for it being a particle or a wave, but one piece of evidence that I didn't mention was the polarization of light. And this is a phenomena where if light travels through a crystal or a medium or it reflects off an object, sometimes it loses intensity depending on the angle that it hits the object. Now, Newton argued that a wave doesn't care about what angle it hits objects, like a sound wave, but particles, depending on which side they come into contact with, they could interact differently if they've got a certain shape. Just to show you what I'm talking about here, I've got a couple of pairs of 3D glasses that are polarized. And you can see that, yes, you can see through them. You can see through this one as well. You can see me in both. But if I hold this one, there you go, up here, and I show you this, look, if you look through both of them, it's completely black. But separately, they're both completely see-through. So it's only when they're covering up each other that the darkness is there. Oh, and just as an additional thing, if you change the angle of them, you can see through them a bit more, although it is a bit hard for you to tell. It is a bit dark. It definitely gets darker like this, and you can see through them a bit more like that. There you go. This is a better example there. Okay, so how is that happening? What does this tell us about the nature of light? So polarization comes from the fact that light is a transverse wave, and this is what they discovered by understanding polarization. Light is transverse, so it can be traveling up and down like this, in which case, if you have a polarized lens, like in these, if those lenses have gaps in them, which are also arranged in the same shape as the light, then the light can freely travel through the gaps like this. But you can imagine if we had light that was going back and forth, it would get blocked by these gaps. So depending on the angle at which the light's coming through, then it either gets blocked or it's allowed to pass through. If we change the angle of the polarized light, so now the light was coming across like this, now you can imagine the green light being able to pass through while the red light is essentially blocked by this barrier. This is what's happening with the glasses. Now, sunlight is a mixture of light of all different polarizations. So we have some upwards light, some sideways light, and all the angles in between, all on top of each other. If it passes through a filter, then on the other side you only get light that's in phase with that filter. You only get light that's polarized at the same angle as that filter is. If you then put another filter in front of it, going the other way, then you will block all of that light. What this means is you'd be able to see through one polarized filter. You can even see through two if they're polarized in the same direction, but if they're polarized in opposite directions, you cannot see through either. So again, I'll show you examples with this. Can't see through, there you go. You can see through that, and if I change the angle, you can't see through that anymore. So here, they're both pointing in same or similar directions, but if I do this, now they are pointing in opposite directions, blocking more light. Okay, how does this relate to Malus's law? His law talks about the angle. So if the original beam of light is up down like this, because it's been polarized with a completely vertical polarized lens, then the amount of intensity that it's going to keep transmitting forward if it goes through another filter depends on the angle of that filter. So the angle of this one was completely vertical, right? The polarized light is polarized in a completely vertical angle. Now, if we introduce a new filter that is at some angle theta to the original polarization, then we're going to lose some of the intensity of the light. In fact, the intensity that we get, I, let's bring this forward. Okay, the intensity that we get, I, is going to be equal to the maximum intensity, that is the intensity coming through here. This is I max times cos squared theta, where theta is that angle. So the closer that angle is to 90 degrees, the closer your new intensity is going to be to zero. The light coming through now, its intensity is going to be zero if this is 90 degrees. The closer it is to zero, so the closer they both line up with each other, the closer I max is equal to the new intensity. You get all the light coming through. And that's pretty much it. Once they realized that light was transverse wave, then that allowed them to use the wave nature of light to understand polarization, and we learned a lot more about polarization from that.